The predominant theory, according to most scientists, is that current explanations for the nature of the universe still focus primarily on its origins. The most prominent account of its early evolution is a theory that links the creation of planets and stars, events that eventually gave rise to life, including humans. Despite its odd name, the Big Bang theory is a comprehensive explanation of what could have occurred when the universe was first created. In its infancy, the universe was contained within a remarkably insignificant space, much smaller than a pin, and packed with extremely compressed particles. A massive explosion of energy and matter, known as the Big Bang, took place billions of years ago. This catastrophic event marked the vast beginning of the universe. However, as scientific information grows over time, inconsistencies begin to emerge, calling into question the assumptions that underpin this hypothesis. At the time NASA launched the James Webb Space Telescope, JWST, the most advanced space observatory ever built, professionals anticipated that its evidence would support the Big Bang theory. However, within the first year of operation, scientists were astonished by the telescope's remarkable ability to look deep into the universe's distant past. The JWST's innovative capabilities revealed galaxies so old they challenge our existing knowledge. This revelation, about the origins of the universe, has sparked lively discussion about the possibility of matter existing even before the Big Bang. A substantial turning point occurred when cosmologist Rohan Nottu, analyzing JWST data, discovered a newly formed galaxy shortly after the Big Bang. It was designated the most distant galaxy ever observed. This discovery shocked the entire scientific community and highlighted the remarkable capabilities of the James Webb Space Telescope. The JWST's ability to alter our perception of the universe is just beginning. It is bringing fresh perspectives to the universe's earliest stages. Right now, it connects, albeit loosely, to previous cosmic events and holds the key to understanding the formation of the first stars. The JWST's findings have revealed galaxies with characteristics that defy previous expectations. The sudden appearance of early galaxies has sparked intense scientific inquiry. Researchers are working to incorporate these new results into established models. As they continue investigating, they encounter fundamental questions about the very nature of the universe and the forces that shaped its development. The JWST's impressive contributions to science are made possible by its strategic location. 1.5 million kilometers from Earth, protected from interference and kept near absolute zero by a sun shield the size of a tennis court. This setup enables continuous, undistorted observations beyond the Earth's atmosphere. Equipped with a huge front-view mirror and sophisticated instruments, the JWST was specifically constructed to gather information about the early universe, data that was previously out of reach. This early era, known as the Cosmic Dawn, began between 200 and 300 million years after the Big Bang. It marked the formation of the first galaxies and stars. The processes behind this formation remain a central focus of theoretical research, including the roles of dark matter, dark energy, gas interactions, and cosmic dust. By observing galaxies from this pivotal era, cosmologists have a rare opportunity to test current universe models. Studying these ancient galaxies allows scientists to either confirm existing theories or uncover their limitations, discoveries that could lead to groundbreaking insights. Initially, JWST was expected to find only a few small, faint galaxies. However, its observations far exceeded expectations. The telescope's first deep-field images revealed a staggering number of galaxies varying in size, age, and luminosity, much more than predicted. This unexpected abundance has sparked a race among astronomers to reassess data from the universe's earliest large-scale structures. New discoveries continue to pour in, stunning even the most seasoned scientists. Both experts and the public have shown great interest in the JWST's advanced capabilities. Some researchers have proposed that flaws in the telescope's operations or in how we interpret large-scale observations might explain some of the surprising outcomes. Still, the general consensus is that the results represent a paradigm shift in our understanding of the early universe. These early revelations raise significant questions about the universe's complex and challenging nature. Some researchers are trying to fit the findings into existing frameworks, while others suggest they point toward a more mysterious and intricate cosmos than previously envisioned. One critical question remains: how did the known universe emerge from the chaotic conditions of its earliest stages? The JWST's early findings could significantly alter our perception of the Big Bang, offering fresh perspectives that go beyond ancient cosmic rays and distant galactic structures. These findings may even impact our understanding of our own Milky Way galaxy. Mark McFadden, a senior research scientist at the European Space Agency, remarked that such machines are not built to support theories, they are made because we have no idea what we'll find. The story begins in 1985, when the Space Telescope Science Institute, STSCI, started planning for a successor to the Hubble Space Telescope. At the time, Garth Ware led STSCI and was tasked with imagining what would come after Hubble. Though initially met with skepticism, Ware and a small team laid the foundations for what would become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, JWST was designed to view the universe in infrared, allowing it to peer deep into space. This capability is essential for observing distant galaxies whose light has been stretched due to the universe's expansion, rendering them invisible to optical telescopes like Hubble. The JWST's large, star-like, icy mirror has become an indispensable tool for uncovering the mysteries of the universe's beginnings. The need for such a telescope became clear in 1995, when the Hubble Deep Field image revealed an abundance of galaxies in what was previously considered an empty patch of sky. That discovery underscored the need for a more powerful telescope capable of looking even further into space. After years of development and a nearly $1 billion investment, the JWST launched on December 25, 2021. By July 2022, it was ready to begin its critical scientific mission. Programs like the Early Release Science, ERS, and the General Observations Program were designed to look for early galaxies. Once again, the results far exceeded even the most modest expectations. JWST's observations have already begun challenging traditional models of the early universe and revealing galaxies that defy established cosmology. These groundbreaking discoveries highlight the importance of pushing the boundaries of scientific exploration. They also showcase the extraordinary potential of cutting-edge technologies like the James Webb Space Telescope. Researchers continue to analyze the data, and more revelations may come, further transforming our understanding of the universe. When the first JWST data started arriving, cosmologists eagerly awaited the results. Many had spent years preparing their systems for data analysis, rather than relying solely on traditional peer review, which can take months. Yet, the discoveries made by JWST suggest that we may need to revise or expand that foundation. While the Big Bang Theory still explains the broad strokes of how the universe began, from a dense, hot singularity to the rapid expansion and cooling that allowed matter to form, what JWST is uncovering are the fine details, the unexpected complexities, and the gaps in our understanding that cannot be ignored. For instance, some of the early galaxies observed by JWST appear to be too massive, too structured, and too luminous to have formed so soon after the Big Bang, according to current cosmological models. These galaxies challenge the timeline of cosmic evolution and suggest that galaxy formation may have started much earlier or proceeded much faster than we thought. If that's true, then the very sequence of how stars, galaxies, and larger cosmic structures emerged might need to be re-evaluated. This has given rise to new theories and hypotheses. Some researchers propose modifications to the standard model of cosmology, such as tweaks to the rate of expansion or the influence of dark matter. Others are exploring entirely new ideas, including models of a cyclic universe, or multiverse theories where our Big Bang was just one of many such events. Moreover, the role of dark energy, the mysterious force accelerating the universe's expansion, is also under renewed scrutiny. JWST might help scientists measure its effects with more precision or even uncover signs that this energy behaves differently than previously believed. In the long run, such insights could bridge the gap between cosmology and quantum physics, two fields that have long remained disconnected in explaining the origin and fate of the universe. Still, it is crucial to remember that science is a process of iteration. Each new observation, especially those that surprise or confuse us, is a step forward. The James Webb Space Telescope is not merely a tool for confirming what we think we know, it's a window into the unknown. It challenges us to ask better questions, to refine our models, and to remain open to possibilities we hadn't imagined. As of now, JWST is just getting started. Its mission is scheduled to continue for many more years, and with every image it captures and every spectrum it analyzes, we move closer to a deeper, more complete understanding of the cosmos. The sky is no longer the limit. It's the beginning. Understanding the cosmos's early stages, this theory proposes that stars, planets, and eventually life, including human life, emerged as part of the universe's evolution. Despite the oddity of its name, the Big Bang Theory offers a coherent explanation of the universe's earliest moments. Initially, the universe existed as a singularly dense point, far smaller than a pinhead, filled with densely packed particles. From this compressed state, a massive release of matter and energy, the Big Bang, unleashed forces that would shape the universe. This enormous event, occurring billions of years ago, set the course for the universe's unfolding story. As our scientific understanding progresses, however, discrepancies have surfaced that challenge long-held assumptions. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory ever built, there was an expectation that its data would validate the Big Bang theory. Yet, within just 1 year, the telescope amazed scientists with its unprecedented ability to peer deeply into the universe's distant past. The JWST's groundbreaking capabilities have uncovered galaxies that challenge current theories, forcing scientists to reconsider our understanding of the universe's formation. This has prompted discussions on the potential existence of pre-Big Bang matter. The breakthrough came when cosmologist Rohan Natu, analyzing JWST data, discovered a galaxy that formed shortly after the Big Bang. This discovery marked the farthest galaxy observed to date and sparked excitement in the scientific community. The vast potential of the JWST to reshape our view of the universe is just beginning to unfold. With significant revelations about the earliest stages of cosmic history, this period, loosely connected to prior cosmic events, is critical to understanding the formation of the first stars and galaxies. The JWST discoveries have defied expectations, revealing galaxies with characteristics that challenge existing models. The growing influx of early galaxies has prompted a frenzy of scientific inquiry, urging researchers to reconcile these findings with established theories. As scientists delve deeper into these findings, they are confronted with profound questions about the nature of the universe and the forces that shaped its evolution. Beyond its scientific contributions, the JWST's strategic location, 1.5 million kilometers from Earth, shielded from interference and kept at near absolute zero by its sunshield, provides a unique advantage for making uninterrupted observations of the universe. Equipped with a large primary mirror and advanced instruments, the JWST is specifically designed to capture details about the early universe that were previously impossible to detect. This early period, known as the Great Dawn, began 200 to 300 million years after the Big Bang, marking the formation of the first stars and galaxies. The mechanisms behind this process remain a central focus of research, with various theories exploring the roles of dark matter, dark energy, and the interactions between gas and dust in star formation. The JWST's ability to observe galaxies from this pivotal era presents a unique opportunity for cosmologists to test their models of the universe's early stages. The JWST findings have exceeded expectations, unveiling a staggering number of galaxies of varying ages, sizes, and luminosities. This has sparked a race among astronomers to revise the records for the earliest known massive galaxies. As the discoveries continue, even the most experienced scientists are left in awe. Both experts and the general public have become captivated by the features of these early galaxies. While some researchers have questioned the telescope's interpretation of large-scale observations, the prevailing view is that these findings represent a paradigm shift in our understanding of the early universe. The recent discoveries made by the JWST have posed significant challenges to traditional cosmological models, prompting scientists to consider the possibility of a far more complex universe than previously imagined. The pivotal question remains: how did the universe emerge from the chaotic conditions of its early stages? The JWST's findings could dramatically reshape our understanding of the Big Bang and provide new insights not only into distant galaxies and ancient cosmic structures but also into the nature of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, put it, "You build these machines not to confirm theories, but to break them." The origins of the JWST trace back to 1985, when the Space Telescope Science Institute, STSCI, began planning for a successor to the Hubble Space Telescope. Despite initial skepticism, the small team at STSCI laid the groundwork for the JWST, which would eventually surpass Hubble by observing the universe in the infrared spectrum. This capability has proven essential for studying distant galaxies whose light has shifted into the infrared due to the expansion of the universe. The need for a more powerful telescope became clear in 1995 when the Hubble Deep Field Observation revealed a vast number of galaxies in a previously thought to be empty region of the sky. This discovery underscored the need for a telescope capable of probing deeper into space. After years of development and a significant financial investment, the JWST was launched on December 25, 2021. By July 2022, it was ready to begin its critical year of scientific exploration. The results from the JWST have already begun to challenge long-standing assumptions, unveiling galaxies that defy conventional cosmological models. These groundbreaking discoveries emphasize the importance of pushing the boundaries of scientific exploration and the extraordinary capabilities of technologies like the James Webb Space Telescope. As researchers continue analyzing the data from the JWST, new insights may emerge, expanding our understanding of the universe. When the first data arrived, cosmologists eagerly awaited the results, having spent years preparing their systems for this moment. The first wave of images and measurements stunned the global scientific community. They revealed an intricate cosmic tapestry filled with unexpected structure and complexity, far earlier in the universe's timeline than previously predicted. Galaxies appeared to have formed faster, grown larger, and organized themselves in ways that contradicted long-standing models of gradual evolution. These revelations ignited debates among cosmologists and astrophysicists. Could it be that the universe matured more rapidly than we thought? Or do our models need fundamental revision? Among the most astonishing findings was the identification of massive, well-structured galaxies existing just a few 100 million years after the Big Bang. Traditional models had predicted that such galaxies would require billions of years to form, accumulate mass, and take shape. Yet the JWST was capturing them already mature and luminous in the universe's infancy. These observations suggested either unknown forces at work in early cosmic evolution or the possibility that our current understanding of time, expansion, and cosmic distance may be incomplete. To address these puzzles, teams across the globe are collaborating on unprecedented scales. Supercomputers are now running new simulations, incorporating the latest JWST data in attempts to adjust existing models or even develop new ones altogether. Theories about dark matter behavior, cosmic inflation, and the fundamental constants of physics are being revisited and rigorously tested. At the same time, the JWST continues its mission, expanding its reach into the most remote corners of space. Each new observation adds another piece to the cosmic puzzle, revealing nebulae shaped like celestial sculptures, stars forming in clouds of gas and dust, and the gravitational fingerprints of unseen matter warping the very fabric of spacetime. Beyond the raw data and scientific insights, the images returned by JWST have had a profound cultural and philosophical impact. Vivid, breathtaking glimpses of the early universe have rekindled a collective sense of wonder, reminding humanity of our small yet significant place in a vast and ancient cosmos. As the telescope peers further, humanity itself steps deeper into an age of discovery that may reshape not only our knowledge of the stars, but of ourselves.